Hey everyone, welcome back to Game Code Mastery. Today, we are building a flexible action system in C++ that you can reuse across any project. By the end of this action system tutorial series, you'll have a fully working action system in C++ that you can reuse across any project. Let me show you what we are building with this action system and why you should care about this approach. This system will handle all actions such as jumping, dodging, and attacking. This system will also manage when different actions should block each other, when they can combo, and how they interact with and manage your character's state. For example, controlling if you can attack while dodging or while in the air. Another example is a special state that activates a certain animation in your animation blueprint, and can also tell the action system to activate a special attack action if the attack is activated while a certain state is active. This will be powered by gameplay tags, which will allow us to create smart relationships between actions. In our action data, we will have things like granted active tags, which are tags granted when the action is activated and removed when the action ends. This, in combination with the blocked tags, determines if the action can activate or not. This will give us a data-driven gameplay tag workflow for managing when actions can be activated and how actions interact with and manage your character's state, all without hard-coded dependencies or long and messy if statements. And because it's built as a reusable component, you can drop the action component onto any actor to give that actor an action system. This is architecture that can scale and grow as your project grows. Now, before we dive in, I want to let you know that this action system is actually the first piece of something bigger. Over the next several tutorials, we are going to be building out a complete Souls-like combat system by creating several standalone systems that all work together perfectly. We'll cover an attribute system for health and stamina, a hitbox system for hit detection, an enemy AI system for challenging opponents, a damage and hit reaction system, a targeting system for locking onto enemies, a weapon system for handling multiple weapons, and more. Each tutorial, including this one, is designed to be completely standalone. You can just follow this action system tutorial and walk away with something incredibly useful for any project. But if you stick around for the whole series, by the end, you'll have all the building blocks for a professional-grade Souls-like combat system. Now, this system won't follow the single responsibility principle perfectly, and that's fine. You don't always need to follow every design rule if it gets in the way of your actual goals. For us, the priorities are simplicity and keeping implementation separate from data. We'll break everything into two main classes. The action class, which will be a base data asset that stores configuration for a specific action. The second class will be an action component, which will be a reusable component that manages actions for an actor and handles what happens when they are activated. On top of that, we'll make use of gameplay tags to filter and organize actions. If you're new to gameplay tags, I recommend you check out my separate video where I cover them in detail. Okay, with that out of the way, let's go ahead and get started. To follow along, all you'll need is a third-person template setup, plus the free Paragon Greystone character from the marketplace. The very first thing we are going to do is create our action class. We can do so by selecting Tools, New C++ class, All Classes, search for a data asset, and select data asset here. Okay, let's name this ACS_action. And we'll put this in the folder action system. And we will make this public. So this will be in public action system. Now, you may have noticed that I'm using the prefix ACS_. Most projects will have a short code or abbreviation in front of their class names. For our project, ACS stands for Advanced Combat System. It keeps everything organized and makes it clear what belongs to this system. So let's go ahead and select Create Class. Okay, and now you should have the class here in your IDE. So yours might look slightly different if you're using a different IDE. So now let's go back to the engine really quickly. And let's create a new C++ class. Let's create that action system component. So put this in the same location, the public action system. Let's call this ACS_action system component. And let's go ahead and create class. All right, now let's go ahead and close out the engine because we are going to write some C++ code now. So it's a good idea to close the engine so that way when we finish, we can compile and open the engine. We could also use live coding, but I'm not going to do that because I've found live coding can sometimes corrupt blueprint files. So I'm probably going to stick to mostly just compiling from the IDE. Now let's go ahead and remove these comments. We won't need them. Let's go to the CPP file, remove the comments. We can also remove tick completely because we won't be using that. Let's go back here and just remove tick. Now, as I said earlier, we are going to make use of gameplay tags to filter and organize actions. So in order to use gameplay tags in our code, we are going to need to be sure to include that in our project. So we need to find our build.cs file. It should be in source, project name.build.cs. So you just need to make sure that you have gameplay tags added here. So if you don't have it, you would just add this exactly as I have it here at the end of your add range or your public dependency module names. The reason why we need to do this is because Unreal won't compile our project with gameplay tags unless it knows our code depends on that module. Adding it tells the engine that we need this module's functionality. In our case, it is the gameplay tags. Think of it like adding a library to your project so you can call its functions. Without it, the compiler has no idea what fGameplay tag is, for example. Now let's go work on our action class here. So let's start by adding a public section here. And this is something known as an access specifier. Access specifiers control who can see and use different parts of your class. You can think of them like security levels for your class members. Public means anyone can access members from anywhere in your code. A good practice is to start with private or protected by default and then make things public only when other code needs them. This keeps your classes clean and prevents accidental misuse of internal components. In our case, the reason why we are making this public is because we are going to want to access all of this from our action system component. So because of that, we are going to make it public. Now, let's add a uProperty. If you don't know what a uProperty is, the uProperty is a macro that tells Unreal Engine to manage your C++ variables, making them work with blueprint, serialization, garbage collection, and the editor. Marking a variable as a uProperty will also expose your variable with Unreal Engine's reflection system, so that the engine knows that the code exists and can manage it properly. Unreal Engine's reflection system allows the engine to examine and evaluate itself at runtime. This enables things like automatic garbage collection, exposing our C++ to blueprints, editor details panels, and more. In our case, we are going to expose this to the editor. So we are going to make this edit anywhere, which means that this property will show up in the editor details panel and also in instances as well. And then we are going to specify the level of blueprint access that this has, blueprint read only. And then category is going to equal action. And this will be a fGameplay tag, action tag. You may have noticed that the fGameplay tag here is red. And if you tried to compile this, your code actually wouldn't compile. That is because we need to include gameplay tag container. So let's go ahead and do that. Hash include gameplay tag container.h. And now fGameplay tag container is no longer red. If you don't know, hash include is a preprocessor directive that literally copies the contents of the specified file into the current source file where the hash include line is. This happens during the pre-processing stage, before the compiler translates your code into object code. The reason we need to include gameplay tag container is because that is where fGameplay tag struct is defined. Also because we are using the gameplay tag type directly by value. Now let's add a comment here so we can explain what this is used for. Action tag to find an action by tag without a reference to the object. Now let's add another U property. Actually, we can just copy and paste this. This will be f gameplay tag container. So this will be a gameplay tag container, and this one is a single tag. So a gameplay tag container just allows you to add multiple tags. We will call this one granted tags. And let's add a comment here to explain what this is going to be used for. And if you don't know what this is going to be used for, this is going to be tags added to owning actor when action starts, removed when action stops. So these tags are going to be granted and removed when the action starts and stops. This will be useful for allowing us to know if a specific state should be active while an action is active. So for example, we could say that the attack state is active while the player is performing the attack action, which will be very useful for us later when we are building out our action system. And actually, instead of blueprint read only, for this one, I'm going to remove that. That way you can't read or write from blueprint. Now let's copy this and paste it here. And this will be an f gameplay tag container blocked tags. Let's add a comment to explain what this will be used for. Action can only start if owning actor has none of these tags. So what this will allow us to do is, let's say for example, you don't want to allow attacking while dodging. Well, what we could do in this case is create a state for attacking and dodging. And we can create those states as gameplay tags. And then we can add those to the granted tags for each of those actions. For the dodge action, we can be in the dodge state. And so in our attack action, we can add dodge state to the blocked tags. So that way, dodge will block attack from being able to activate, which is going to be very useful for our action system. Now, let's add void start action. And actually, we will need to make this virtual void start action. And virtual is just a keyword that you put on a function in a parent class to say that child classes can override this function if they want to, which allows different classes to have their own version of the same function. So you should use the virtual keyword for any function that you think will need to be overridden in a child class. A good practice is to not make them virtual by default, and if you need to override them in a child class, then you can make them virtual. Otherwise, there's no need to make it virtual. In our case, we are going to need to make this virtual, so each action can have slightly different functionality. I'm also going to add a virtual void stop action. Now, since our action is a data asset and is going to be used primarily for data configuration, the only thing that our stop action and start action functions are going to do is call functions from the action system component. So that means we are going to need a reference to our action system component in our action. And an easy way to do that is to just pass it as a variable in our function. So let's go ahead and do that. So let's go ahead and add UACS underscore action system component as a variable here. We will make this into a pointer. Call this action conf. To make a variable into a pointer, you need to use the asterisk symbol in the declaration like I have here. I recommend you already be familiar with pointers as they are essential fundamental concepts for Unreal C++. But for clarity and understanding, I will provide a brief summary of pointers in C++. A pointer in C++ is a variable that stores the memory address of another variable, rather than storing a value directly. You can think of it like a street address that tells you where to find a house, rather than being the house itself. It's a more efficient way to pass objects around without having to keep recreating copies. So instead of recreating copies of the object, you only need to pass around the address of the object, which is much more efficient. Now, if we try to compile this, this will actually give us a compiler error because the compiler won't know what action system component is. Now, you could fix this by adding an include up here, but I don't recommend doing that. A good practice is to use forward declaration in headers when you only need pointers or references. Save the actual include for your CPP file where you will actually need the full class definition. For declaration tells the compiler this class exists without including its full definition. Think of it as promise now, deliver later. This creates less bloat, so we will have faster compile times, and reduces dependencies as we will only be including them when we actually need them. This also prevents something known as a circular dependency, which is when two or more pieces of code depend on each other, creating an infinite loop that breaks compilation. Now, some things to note about how forward declaration works. Now, there are two ways that you can forward declare a class. You can do it exactly where it's needed, like this, and then I'm going to go ahead and copy that, paste it, and here we no longer need to forward declare it. This forward declares it for this line and every line below, not above. Because of that, I'm going to go ahead and copy that. To actually do it up here at the top of your class. So class, and then the class name here. Now we can remove that from here. You should do it this way if you're going to be using it multiple times in your header file, like we are here. Okay, now let's add another function, virtual bool can start action. So this is going to check if the action can be started. This will allow us to control when the action can be started. So I'm going to copy this and add the action component to this one as well. Virtual bool can stop action. This one will allow us to control when the action can be stopped. So that way, if we want to prevent starting or stopping the action during certain gameplay scenarios, we can do that using these functions. Let's also add a bool does satisfy tag requirements. And we are also going to add the action component here. It will also be a good idea for us to make some of these const. So can start action should be const, can stop action should be const, and does satisfy tag requirements should also be const. If you don't know what const is, const makes variables, parameters, or functions read only. This is useful for letting people know that this function is read-only and should not modify state. In our case, can start action will only need to check if the action could be started. Same for can stop, and does satisfy tag requirements is only going to check if the tag requirements have been satisfied. So these are essentially just functions that check things and they do not change things. So we can make them const. Be sure to add definitions for these functions, because if you don't, then your project will not compile. So I'm going to go ahead and do that. And for can start action, we're going to need to return a value. So let's return true. Let's do the same thing for the other ones as well. So now the next thing we are going to do is add an animation montage to our actions, because our actions will need to have animation montages associated with them. So that way, for example, the dodge action can play the dodge montage whenever it is activated. So what we are going to do is let's create another U property. Edit anywhere, category equals action. Make this class. So we're going to forward declare it here because this is the only place we are going to need it. UM montage pointer action montage. Now we will also need some other values associated with our montage. So let's copy that. And this one will be a float. This will be the play rate. Make that equal to 1.f by default. So we're going to initialize this by default as 1. Paste that here, and let's make this into a T array. This will be a T array of if names, and this will be the montage section names. So these will be the montage section names associated with this action montage. Now above this one, actually, let's create another variable. Let's make this a bool, b random montage section. By default, this will be false. And this will allow us to specify if we want to use a random montage from our montage section names. So by default, it will get from the first index, but if b random montage section is true, then we will grab a random montage section name from this array. Now you might have noticed that we used tarray here. Tarray is Unreal Engine's dynamic array. It's a list that can grow or shrink at runtime. The T here in front of the tarray stands for template. And anytime you see a T prefix in Unreal Engine, it means this is a template class, which is generic and adaptable, meaning it can hold any type of data, like ints, floats, or custom objects. You may have also noticed that we have b here in front of our Boolean variable. That is also standard practice in Unreal Engine to include b in front of your variable name for Booleans. That's just b for Boolean. And you also may have noticed things like f in front of f gameplay tag container and f gameplay tag. This simply indicates that it is a struct. So those are just some standard naming conventions used within the engine. Now, something that you may notice is that all of these variables are related to each other. So since all of these variables are related to each other, it might be a good idea to make these into a struct. Because when you find yourself passing the same 3 or more variables around together frequently, they might belong in a struct. A struct groups related variables together into a single data type, which is like creating a custom container that holds multiple pieces of information as one unit. So let's go ahead and create our f-action-montage struct. Let's cut these variables. You might be wondering, where should we define our struct? Well, we can define our struct here in our action. And the reason why is because we know our action-montage struct is only going to be used in our action and will not need to be used outside of the action. Now, if you ever think that you will need to use this struct outside of the action class, then it would be a good idea to define the struct in something like a types header file. So that way, you only need to include the header used to define the structs without including the entire class. But in our case, we don't ever plan to use the struct anywhere else, so it's going to be fine to just define that here in the action class. Or at least that's the plan for now. We can always change that later if we need to. So let's add a U struct to be blueprint type. So that way we can expose the properties within this struct to blueprint. This will be a struct if action montage. And let's add generated body here, because you need to add generated body to structs. If you want to know what this is essentially a macro that if you hover over it, you can see Unreal Engine replaces this with all the necessary boilerplate code that gets generated for the type. So this will just generate some necessary code for our struct. So now we can paste all of those variables that we created earlier right here. Instead of setting these values directly, let's set them using a constructor, or rather an initializer list. To understand what an initializer list is, you must first understand the concept of a constructor. A constructor in C++ is a special type of function that runs automatically when you create an object, and its job is to initialize that object's data. So a typical constructor looks something like this. Type in the name of your class, or struct in our case, f-action montage, open and close parentheses, and then curly braces. And here you can set the default values, such as action montage equals null pointer, play rate equals 1.f, and so on. So you just add any variable that you want to initialize in the constructor. However, for structs, instead of defining the default values with a standard constructor, it is actually good practice to define the default values through an initializer list. An initializer list is a special syntax used in constructors to initialize class member variables before the constructor body executes. Using an initializer list is considered best practice because it constructs a variable with the intended value from the start rather than default constructing it and then assigning a new value in the constructor body. This is also consistent with Unreal Engine standards, Unreal Engine's coding style often prefers initializer lists for clarity and performance. So let's follow those Unreal Engine standards and good practices by creating an initializer list. The way to do that is action montage. So that's the name of your struct, and then open close parenthesis, and let's add colon, and then the name of the variable that you want to initialize, action montage, and then in parentheses here, let's initialize our action montage as a null pointer, null PTR, and for the ones below the first one, add a comma, and then variable name, play rate. We're gonna make this 1.f, comma, the random montage section be false by default. Let's do the montage section names. We can just initialize this as an empty array. After that, let's add open close curly braces. One benefit to creating a struct in C++ compared to Blueprint is that you can add functions to structs in C++. So let's take advantage of that by adding a few helper functions to our action montage struct. One useful helper function to have will be to know if the montage is valid or not. So let's type in bool, because this is going to return a boolean, and call this is montage valid. We will make this const, and this will return if action montage is not equal to null PTR. And the next helper function will return the last section index. We need to return an int32, get last section index. And this one will be const. And the way this is going to work is it's going to return montage section names. So this is the montage section names array that we created earlier. And we are going to access this array with the dot operator. If you don't know what the dot operator is, in C++, the dot operator is called the member access operator, which is different from things like the scope resolution operator and the arrow operator, which we will talk about more later. But essentially, the dot operator is used when you have a direct object instance. In our case, we created an array variable of fnames, which created an instance of that type. And since we have direct access to the instance, we can use the dot operator to access its members. And this one has a member that we need to access, .num, and then we need to do -1. The reason why we need to return the montage section names as num -1 is because of the way arrays work in Unreal Engine C++. The first element in an array starts with index 0. The num function returns a number of elements in the array. For example, an array with 4 elements will return 4, because the index is 0, 1, 2, 3, which is 4 elements, but the last index will be 3. That's why we need to subtract 1 from num to get the last index for the array. Okay, and the next helper function is going to be an int32, and this one will get rand section index. This will be const, and right at the start, we are going to check if montage section names dot. We're using the dot operator, and we are going to access a function in the array. This is empty. This lets us know if the array is empty. And if it is empty, you're going to return 0. Or actually, we could return -1. That way we can know this failed. Okay, and now we are going to create a local variable, which is going to be an int32, be a rand index. And we are going to have this equal fmath, and we are going to use the scope resolution operator. The scope resolution operator accesses members of a type itself. Scope defines where something can be accessed in your code. And the scope resolution operator is used to define or access members like variables, functions, or classes that are outside the current scope. In our case, we don't have a direct object instance of fmath. We are going to access its member functions by using the scope resolution operator. And we are going to use rand range. We can use a keyboard shortcut in Visual Studio. If you're using Writer, you can set the key map to Visual Studio keyboard shortcuts. Pressing Ctrl-Shift-Space shows us the inputs for the function. In this case, we have a min and a max. So the min will be 0, and the max will be get last section index. Now we don't plan to change this later, so it will be a good idea to go ahead and make this const. Okay, and now we need to check if montage section names, you're going to use a function called isValidIndex. You're going to check, is the rand index a valid index? We actually are going to check, is it not a valid index? So we are going to use a not operator here. And the not operator basically flips a Boolean value to its opposite, turning true into false and false into true. Essentially what we are doing is we are returning if the random index is valid. If it is valid, then that will make this false. If it is not valid, it will make this true. In which case we can return -1. And if we make it this far, we can return the rand index. And the last helper function we are going to create is going to be used to get a montage section name. So this will return an f name. This will be get montage section name. And this will have an input variable, const int32 section index. This will be a const function. Okay, let's check if montage section names is empty. If it is empty, we return name underscore none, which if you don't know what that is, this is a global variable, which is essentially a special 0 value, meaning no name. Now let's create an int32 selected index, and this will be equal to section index. And since we have a Boolean, be random montage section, since we have that Boolean, let's go ahead and use that. Be random montage section. If that is true, then the selected index is going to be equal to get rand section index. Then we're going to do a check if, and this check will do a similar check that we did before, is this one. We're going to copy that and paste it here. And instead of the rand index, let's use the selected index. So if the selected index is not a valid index in the montage section names array, then we return name underscore none. And if it makes it this far, then that means we have found a valid section name. We can return montage section names. And to access an array, we can use brackets like this and the index inside the brackets, which in our case is selected index. Okay, and that should be all the helper functions we need for this struct. The next thing we need to do is go down here to the blocks tags, right underneath that, and let's create another U property. Let's make this, to make this one similar to the U property we used up here for the action tag. And this will be an if action montage. Before we compile our code, let's make an improvement to our DoesSatisfyTagRequirements function. The only thing this function will need to do is check the active gameplay tags from the action system component. And since we will only be calling this function from the action system component, we can simply pass the action system component's active gameplay tags through this function instead, because we don't need to access the action component just to check the tag requirements. What we are going to do is replace this with if gameplay tag container. Let's call this active gameplay tags. While this is cleaner, this is also less efficient, because if you pass a variable into a function by value, the program makes a full copy of the data. That's why in C++, and especially in Unreal Engine, it's good practice to pass large data types, like structs or classes, by reference. We can pass by reference by adding an and sign here. Passing by reference is more efficient because it avoids copying data. You are giving the function direct access to the original memory instead of making a duplicate. But since you are working with the original memory instead of making a duplicate, this means any change you make to the reference will reflect back to the original value. This can be useful if that's what you want. However, it could potentially be dangerous if unintended. This is because modifying a reference can lead to data being modified in places it was never meant to be modified, which can lead to unintended bugs and issues that can be hard to track down. However, you can fix this by using const references, because const does not allow the value to be modified. This gives you the efficiency of referencing without the risk of accidentally changing anything. It is safe, efficient, and a best practice way to write your code. In fact, this is a technique that Epic often uses in the engine code as well. So let's go ahead and make this const and make use of that ourselves. And let's copy all of this. And here in action.cpp, let's paste it here. Okay, and instead of simply returning true, let's actually make this do what it's supposed to. Let's return if the active gameplay tags dot operator has any. This function checks the active gameplay tags that we pass into this function has any of these tags. It would be the blocked tags. And we want to make sure that it does not have any of the blocked tags. So let's add a not operator here, because the intended use of this function is to check if the tag requirements are satisfied. In this case, the tag requirements are only going to be satisfied if the active gameplay tags does not have any of the blocked tags. Okay, let's go ahead and compile by holding Control F5. Should compile and launch the editor. Mine compiled successfully. If yours didn't compile successfully, then you may have made some minor mistake. Just note that in C++, everything needs to be precisely correct. If you made any sort of minor mistake, then yours may not compile. So I'm going to go ahead and scroll through my class so that you can reference it and see if you made any mistakes. Okay, here in the engine, in your project folder blueprints. Now you don't need to use the exact same names that I do, just whatever your project folder name is. In blueprints, create a new folder, call it actions. These will be our project specific actions. That's why we are going to put it in our project folder blueprints. Okay, here in the actions folder, miscellaneous, data asset, and here we can see ACS action. Select and call this jump action. Okay, let's open that up. This is what an action looks like in the editor by default. This is all the data that we have. And if we hover our mouse over, you can also see those comments that we added in the C++. You can see that the action tag is used to find an action by tag without a reference to the object. Granted tags are tags added to owning actor when action starts, removed when action stops. Block tags, action can only start if owning actor has none of these tags. That way, anyone filling out this data can easily know what these are used for. This is going to be an example jump action. For the action tag, we can add a tag by selecting plus. Source will be default gameplay tags, action.type.jump. And once you've created that, select action.type.jump. You may have noticed that I created a normal attack tag as well. We do not need that right now. Right now, we only need the jump tag. And if you need an action montage, you can select one. And if you need montage section names, you can add them here. We can set the play rate, and if we want a random montage section or not. For our jump action, we will not use an action montage, so we can leave that blank. In the last video, we covered the design of our action system and implemented the action class, which is a base data asset that stores configuration for a specific action. In this video, we are going to build the action system component, which will be a reusable component that manages actions for an actor and handles what happens when they are activated. On top of that, we'll make use of gameplay tags to filter and organize actions. If you're new to gameplay tags, I recommend you check out my separate video where I cover them in detail. Okay, with that out of the way, let's go ahead and get started. Let's get started with actually building our action component. To follow along, you'll need to complete part 1 of this tutorial where we created and implemented functionality for the action class. We also created the action system component in that video, but didn't add anything to it yet. So that's what we are going to do in this video. If you did not create an action system component, you can simply open your project and create a new actor component class and name it ACS Action System Component. The only thing we've done to our action system component so far is remove some of the default auto-generated code, like the default comments and tick functionality. Something else I would like to do is slightly change our naming convention for our classes. For large projects, this might be more trouble than it's worth, but since this project is small, it won't be a big deal to change it. This will actually be a good opportunity to show you how to rename a C++ class in Unreal Engine. So you see how we have ACS underscore as a prefix for our class names. we're going to be removing the underscore. The reason we are going to do this is because in Unreal Engine, a common naming convention when creating child classes is to prefix the child class with the parent class name underscore. So for that reason, I think it would be cleaner for the base class to not have any underscore. Now, before we do that, I want to mention that this is optional. This is just something that I think would be slightly cleaner. If you want to, you can leave it as it is and it won't ever cause any issues. So to rename a class, you simply have to go everywhere the class is referenced and change the name. So let's get started here with actually changing the file names. This might look slightly different depending on what IDE you're using. I'm using Rider, but in most IDEs, you have a sidebar and you can browse your folder structure, find a class. Now you may have here in edit, you may have some properties here. We have rename option, so we can do that. And here we can simply remove the underscore. So let's uncheck all of this because for educational purposes, we are going to do everything manually. So we're just going to do a quick rename. Now, if you're using Visual Studio, this might look slightly different. Or if you can't do it in your IDE, you can always open an Explorer and just change the file name manually for both the header and CPP files. Okay, I'm going to do the same thing here. Remove the underscore. Then for the CPP files, edit, rename. In the action class, it looks like Rider already updated this for us, the ACS action.generated.h. So you need to make sure that your .generated.h file looks like this. So previously it might look like that. You just need to delete the underscore like we have with our class name. And for the for declaration, we need to remove the underscore. And here, we need to remove the underscore. You can search for it, Control F, ACS underscore, just to see if we missed it. And it looks like we have missed a few here. Okay, it looks like that has got that fixed. Now in the CPP file, you can see all of the red here. Let's go ahead and remove ACS underscore here from all of these. Okay, and now let's do the same thing in the action system component. You can see the .generated.h has been updated. So the underscore has been removed. Remove the underscore from here and from here and from here and here, here, and here. Okay, so make sure everything is correct, that the underscore has been removed from everywhere. Looks like everything is correct. You can just do a search for ACS underscore to make sure on each file. So now save all and close out Rider. Okay, here in your project folder, we need to delete some of the auto-generated files. Let's delete binaries, intermediate, drive data cache, and saved. Once you've done that, we need to try to open up the project. It should say the following modules are missing or built with a different engine version, and then the project name module here. Would you like to rebuild them now? Yes. Okay, that worked for me. Now, you may have an issue where you're in blueprints, the action class no longer has a valid class. Nope, it seems like we can't do that. Probably just need to delete it and create it again. So ACS action, select jump action, and for the action tag, action.type.jump. And if you think that the class name is a bit ugly and you don't like this prefix, we can actually change the way that it looks in the editor with a meta specifier. So we can say meta equals, then parentheses, display name equals quotes action. So this can be the display name for our action. Meta specifier keywords are used when declaring U classes, U functions, U properties, U enums, and U interfaces to specify how they behave with various aspects of Unreal Engine and the editor. In our case, we are changing how the name is displayed within the editor with the display name meta specifier. And in the action system component, since it already has a meta specifier, we can simply add a comma here. Display name equals action system component. and make sure your editor is closed and press Ctrl F5 so that we can compile and run the editor to see if our changes worked. Okay, so now let's go to miscellaneous data asset. And as you can see, it says action here. And if we open up a blueprint actor and try to add the action system component, as you can see, it says action system component here. So that's a lot better. Let's close the editor now. Next, let's work on the active gameplay tag functionality. As I explained in the last video, this system will use gameplay tags to create smart relationships between actions. In our action data, we have things like granted active tags, which are tags granted when the action is activated and removed when the action ends. This, in combination with the blocked tags, will determine if the action can activate or not. So let's go ahead and implement the active gameplay tags. Here in the action system component, what we can do is, here in the top public section, we can add a U property, parentheses, edit anywhere. So that way, this property can be edited within the editor details panel and in instances as well. Then here we can have blueprint read only, category equals tags. Now we are going to make this an F gameplay tag container, and this will be the active gameplay tags. As you can see, this is red, so we need to add the include gameplay tag container.h. From the name, you can probably guess what this will be used for. We are going to use this to track the gameplay tags that are active for the action system. So let's create some helper functions to help us do that. First, we are going to create a function for adding tags to the active gameplay tags. Down here in this bottom public section, let's add a new function. This will be blueprint callable. Category is going to equal action system, and this will be void. Add active tags. Now this will be a const f gameplay tag container reference tags to add. I explained const references in the last video, so check that out for more details. But essentially, it's a more professional and memory efficient way to pass data through a function, because we are passing an alias of the data that cannot be modified instead of creating a copy of the data. And then the next one will be the same function. This function will remove tags from the active gameplay tags. So void remove active tags. Const f gameplay tag container reference tags to remove. Now let's right click, generate definition. The same thing for this one. And what this is going to do is we're going to modify the active gameplay tags dot append tags. And the tags that we are going to append is tags to add, then semicolon. What we are doing here is we are simply adding all the gameplay tags passed into this function onto the action system component's active gameplay tags. And here for remove tags, we are going to remove tags removed from the active gameplay tags dot remove tags. And the tags we are going to remove is tags to remove. Next, we are going to work on a way to know what actions can be activated and what actions have already been activated. To know what actions can be activated, we are going to create an array of available actions. The available actions is the array we are going to search when activating actions by tag. So let's create a T-array of type UASC action pointer. But instead of a raw pointer, we are going to use something different this time. We learned about raw pointers in the last video, but that was for local variables. Using raw pointers when declaring U properties is actually not the optimal way in Unreal Engine 5. When declaring a class member that is a pointer to another object, it is recommended to use TObjectPointer instead of raw pointers, which looks something like this. Property TObject PTR arrows. Inside these arrows, you add the type name so that we can tell the compiler what type of object we want the TObject pointer to point to. In this example, let's use UObject for the type name. This is what a t-object pointer looks like. But why is a t-object pointer more optimal than raw pointers for member variables in Unreal Engine? T-object pointer allows the engine to monitor or track when an object is being referenced or accessed through its t-object pointer. This helps during development for things like ensuring the object isn't prematurely garbage collected while still in use, debugging unwanted access, lazy loading support, and more. However, much of these benefits are only useful for member variables. That is why it is recommended that you still use raw pointers for local variables and function variables, because those are intended as temporary references and they don't need the benefits of a t-object pointer. Let's go ahead and make this into our t-array, t-object, tr, and this is going to be for UACS action. And make sure you forward declare it like I have here, class UACS action. And this is going to be the available actions. We also are going to want to keep track of the current active actions. And we are going to do that with another array. It's going to be the same thing, except a different name. This is going to be the active actions. You might be wondering what the difference is between available actions and active actions. Available actions is the list we search when activating actions by tag. If we want an action to be possible to activate, we add it to this array at runtime. For example, a weapon might add its attack actions to this array when equipped. Active actions, on the other hand, keeps track of which actions are currently running. When an action starts, we add it to this array, and when it stops, we remove it. Now let's create some helper functions to add and remove actions for both arrays. So here in the bottom public section, let's create a U function. This will be blueprint callable. Category is going to be action system. And this one will be void give action. As an input to this function, we will add UACS action pointer. We'll call this action to give, or maybe something simpler like in action. We are also going to need a function to remove an action from the available actions array. Let's copy this, paste it here, void remove action, and we can copy this to remove. And instead of in action for this one up here, we can simply call this one new action. And let's do the same thing for the active actions. We can actually copy these, paste them here, and give them different names. Add active action and remove active action. Okay, and now let's generate definition for these. Let's add the functionality. Let's check if not action, if the action is not valid, or not new action. So if the new action is not valid, we are going to return. But before we return, let's do a UE log. So UE underscore log, parentheses, log temp, warning. And let's add a text macro, text, quotes, could not add action, action not valid. That way we log a warning instead of just silently failing. If it gets this far, we are going to get the available actions and add the new action. Now we're going to do something similar here in the remove action, but instead of new action, we need action to remove for this one, and available actions dot remove action to remove. Now we're going to do something similar for add active action, except instead of the available actions, we're going to add to the active actions. Actually, for this one, let's name it clear action. Go ahead and rename that. This one can be clear active action. Clear. Okay. Okay, now for clear active action, we can copy this one, but before we do that, could not clear action. Could not clear active action, not add active action. We need to make sure that this is not available actions, it is active actions. And the same for this one, for add active action, we need to make sure that we are using the active actions. Now let's create a function to search the active actions array and check if the action is active by tag. So let's copy this U function here. This will return a boolean, and we will call this one is action running. And this will take in an if gameplay tag, and we won't make this a const reference. So that way it makes selecting a gameplay tag easier from the blueprint. We will make this const and show context actions. Generate. We can do this with a ranged base for loop. A ranged base for loop is a for loop that automatically goes through each element in a container, like an array, vector, or list, without needing an index. You can think of it like saying, for every item in this box, do something with it. The syntax looks something like this. For, then you need your type here, and then the name, for example, element, colon, and then the container here, which is going to be like the array. And in here, you can use the element. In our case, type is going to be UACS action, and it's going to be a pointer, and then we can still name it element, that's fine. And the container is going to be the active action. Then we can check if element and element arrow operator action tag is equal to action tag. If that's the case, you're going to return true. And here outside the for loop, if we make it this far, we're going to return false. What we are doing here is we are looping through each action in the active actions array using a range base for loop. For each action, we check if it's valid and if its action tag member variable matches the tag passed into the function. If we find a match, that means the action is active, so we return true. If the loop finishes without finding one, the action isn't active, so we return false. You may have noticed the red squiggly lines here. Since we are trying to access members of this object, this class will need to know about that object so that it can access the members of that object. We need to add a hash include action system ACS action.h. And those lines are gone now. And you may have also noticed that we use the arrow operator this time instead of the dot operator. I explained earlier that the dot operator is what you use to access members when you have direct access to an object. And since the action is a pointer, we need to use the arrow operator to dereference the pointer and to access the member on that object. In this case, the action tag member on that object. If you didn't know, the arrow operator is syntactic sugar that combines two operations. The first is to dereference the pointer, which gets the object it points to, and then accesses the member on that object, which is the same thing as doing this. And then adding a star here, which is how you dereference a pointer. And then let's add a dot. It's essentially like an easier shorthand way to do the same thing. We can also make this const, because we do not change it. And we can make this one const as well, actually, because we are not changing this either. Okay, now let's also update the name for our element a little bit by adding a capital letter here, because in Unreal Engine C++, it is recommended that you start your variable names with a capital letter. Okay, and one mistake that we did make actually here, now that I'm realizing it, is for add active action and remove active action, we do not want this to be blueprint callable, because determining if an action is active or not will be exclusive to the C++. Next, we are going to need functionality that actually allows us to start and stop actions by tag. Otherwise, we have no way of selecting an action and controlling what happens when the action starts and stops. So let's go ahead and work on that now. Let's add this function above the isActionRunning here. And this one is going to be blueprint callable like this one. And this one will return boolean start action by tag. Again, we will make this const if gameplay tag non-reference so that it's easier to select in Blueprint. Okay, now let's copy all of this and paste it below, and we can call this stop action by tag. Okay, let's create definitions for both of these. Okay, and we're going to do something similar to this one. We can paste that here, that we can remove this turn true. Within here, let's add an if not operator. For this one, rename this to action. So that way this one is a little bit more readable. Okay, so not operator, action, arrow operator, and start action. We are going to send this. So if it fails, you're simply going to continue. If you don't know what the continue is, it will basically skip the rest of the current iteration and jump to the next iteration of the loop. So that's what we are going to do if the current action element is not valid. And if we make it this far, we're going to get the action, arrow operator, and we are going to start the action. This. Now, since we are calling a non-const member, we actually need to remove const here so that this is no longer const, because this cannot be const if we are calling non-const member functions. Now let's add active tags and granted tags. So we are adding the granted tags to the active tags in the action system component. And then let's add active action. That will be the action. Then after that, let's return true. What we are doing here is we are looping through each action in the available actions array using a range-based for loop. For each action, we check if it's valid and if its action tag member variable matches the tag passed into the function. If we find a match, that means we can try to activate it. Then we are going to check if the action can be started. Since we added the not operator, that means this will only run if the action cannot be started, in which case we continue. As I said earlier, continue skips the rest of the current iteration and jumps to the next iteration of the loop. But since we added the not operator, this only happens if the action cannot be started. Now, if we can start the action, then it's going to get the action here, then call start action on the action, which if we click on this, this is just going to be the function that we added to our ACS action class. And then we are going to add active tags, and the tags that we are adding is the granted tags. And after that, we are adding an active action to the active actions array so that we can know that the action we found is active. After that, we return true because activating the action was successful. And if it reaches the end of the loop and nothing happens, that means it failed, so we return false. For stop action by tag, let's do the same thing, except change it to stop action. So for here, instead of can start, it'll be can stop. Instead of start action, we'll be calling stop action. Instead of add active tags, we'll remove active tags. We will be removing the granted tags. Instead of add active action, it'll be clear active action. Okay, so it looks like we made a bit of a mistake I'm noticing here. So if we were to try this, this actually would not work. So the mistake that we made, if you didn't pick it up, is that we used the active actions instead of the available actions. And by default, there should be no active actions. So if you try to loop through the active actions and activate one of those, that's not going to be possible. So we need to make this the available actions, which are the actions that are available for activation. That's the point of that array. Okay, that should have the start and stop action functionality completed. Next, let's work on a notification system for our action system, because it would be nice to have the ability for other objects to know when certain things happen, like when the active gameplay tags are updated and when an action starts and stops. This will allow us to do things like notify the animation blueprint when the active tags have been updated to control when an animation is playing. This can also be used for things like letting an AI behavior tree task know when an action has started or stopped. But you might be wondering, how are we going to achieve that? We can achieve that through something known as delegates. In our case, we will use a multicast delegate. A multicast delegate allows you to broadcast a single event to multiple objects at once. It is Unreal Engine's implementation of the observer pattern, where multiple observers watch for changes from one subject. Think of it as a radio tower broadcasting to multiple receivers tuned to the same frequency. So multiple observers can listen for an event to happen from one subject. In our case, the action system component would be the subject, and everything that we bound to listen for these events will be the observers. The benefit of this is that the subject's code doesn't need to contain hard-coded references to specific observer classes. Observers can be added or removed dynamically at runtime without changing the subject's source code. The subject just says something happened and then lets the delegate system handle who gets notified, which makes multicast delegates perfect for one-to-many event notifications without tight coupling. This will allow us to notify other objects, such as the animation blueprint or a behavior tree task, without our action system needing to know anything about them. And the syntax for setting up multicast delegates in Unreal Engine is something like this. So we need to go to the top here, make some room, and in all caps, we need to type in declare underscore dynamic underscore multicast underscore delegate underscore, and then the number of parameters. For our first one, we are going to do one param, and then parentheses. Okay, and then here we need to add the name of the delegate prefixed with an F. So for this one, it will be F on action start, and then a comma, and now we need to add our parameter. So in order to add a parameter to a delegate, we need to add the type. In this case, it's going to be F gameplay tag, and then a comma, and then the name, which will be action tag. Okay, now we can copy this, paste it, and change this to on action stop. Now let's paste it one more time, and for this one, it will be F on active tags updated. This will be F gameplay tag container active gameplay tags. Okay, now we need to add them as U properties, which we can do here at the top. U property, and let's make this blueprint assignable. So that way we can assign the event and use it in blueprints. Category equal events. This one is going to be for F on action start. We will call it on action start. We can copy this, paste it, on action stop, F on action stop, paste it again, and remove all of this. F on active tags updated. On active tags updated. Okay, now let's actually put these to use. On stop action by tag. At the bottom here, let's add on action stop dot broadcast. And within broadcast, you can pass in the action tag, which is going to be the local variable here that we pass into this function. And what this will do is broadcast that delegate for us. Like I said earlier, you can think of it as a radio tower broadcasting to multiple receivers tuned to the same frequency. So this is how we broadcast that. In this case, we are broadcasting that the action has stopped, and any observers that are listening for that event will be notified. We can do something similar here for on action start. Broadcast, and we are going to pass in the action tags or action tag. And the next one we need to do is going to be for add active tags and remove active tags. On active tags updated dot broadcast, and we need to pass the active gameplay tags. And this is just on updated, so we need to call that on both. One thing I want to do before we continue is I want to slightly update the names for these functions. I want the naming for these functions to be more similar to some of the ones we have down here. Let's go to the header file here. Let's see if we can actually rename. So this should rename it for us and make it a lot easier to rename the function. I'm going to call it grant active tags. We can uncheck add core redirect because we haven't used the function enough yet for that to be necessary. And this one, rename to clear active tags. See if it's been updated in the CPP. Grant and clear. Yes, it has. So if you used a different IDE or you renamed it manually, just be sure change it here as well as in the declarations and then where they are called as well. In our case, here in start action and stop action. Next, let's implement a way to get a reference to the avatar actor. The avatar actor is going to be the actual pawn that is performing the actions. Various actions may need a reference to this actor, so it's a good idea to implement a way to handle getting and setting the avatar actor. We can do this by creating a private actor pointer called avatar actor, and then we can create accessor functions to operate on that data. Now you might be wondering why we would make our avatar actor property private and then create getter and setter functions. Wouldn't it be easier to put the avatar actor in the public section so that we can operate on it directly? Making a variable private and then creating getter and setter functions to operate on that data is a practice known as encapsulation. Encapsulation is a fundamental principle of object-oriented programming that involves hiding data within a single unit, such as a class, and then creating accessor functions to operate on that data. You can think of it like putting your data inside a locked box. You don't let other parts of the program reach directly into the box, because that could mess things up. Instead, you give the box a set of buttons on the outside. If someone wants to look at the data, they press the Get button, and if they want to change it, they press the Set button. This is both safe and professional practice. Most programming guidelines encourage encapsulation because it makes code easier to maintain, safer to use, and less prone to bugs. So let's take advantage of that good practice in our code. Let's go ahead and do that. Create a private section. Okay, so the first thing we are going to do is go to the top here and forward declare class aActor. Now let's create tObject tr arrows aActor. This will be avatar actor. And we are going to need to add U property to this. This will allow Unreal Engine's reflection system to know about this pointer so that it can handle it properly during garbage collection. And next, let's create the getter and setter functions. We need U function, void set avatar actor. And as an input, we're going to add a actor pointer and call this an actor. We can implement this here because it's going to be very simple. You're just going to set avatar actor as the inActor. Okay, and then let's paste the U function here again. And this time it's going to return a actor pointer, get avatar actor. And it's going to be const, but instead of implementing that here, let's implement this one in the CPP file. And that is because we're going to do something a little bit special with this one. We're going to check if avatar actor is valid. In that case, return avatar actor. But if it makes it this far, that means the avatar actor is not valid. In this case, we're going to return get owner. We actually could just return the owner as the avatar actor, but the reason why we're doing it this way is because this gives us more flexibility. So let's say, for example, you add the action system component to something like the player controller. Well, in that case, the avatar actor would actually be the controlled pawn. You might want to set the avatar actor manually, which you can do by calling this function from your controller, and then when this is called, it will return the correct avatar actor. Next, let's implement a default actions array so that we can give actions to the action system component by default when the owning actor is spawned. This will be useful for actions that we want to always be available to the owning actor. So let's go ahead and do that. Let's add a third array and call this one default actions. And this one will be edit anywhere, and the category will be action system. Okay, now let's put this to use. We should be able to do something similar to what we did down here. So let's just copy this for loop, paste it here in begin play, and instead of active actions, make this default actions, and then let's remove this, give action, and the action we are going to give, let's rename element to action here. Let's give the action. Now you may have noticed an issue here because we cannot convert const UACS action to parameter UACS action. And we can fix this simply by removing const. Now another thing that would be useful for us to do is to create a function to handle playing an action montage. And the reason why we are going to create this function is because handling action montages is one of the things that our action system is going to handle. So it makes sense to create a function to handle playing an action montage. Let's make this one return a float and call it play action montage. The first input will be a class anim montage pointer montage to play. The next will be a const float play rate, and that's going to equal 1.f. The next one will be a const fname reference start section, and by default it's going to equal name none semicolon. Okay, now let's generate definition. Okay, and the first thing we are going to do is check is montage to play not valid. If that's the case, we are going to return 0.f. And if we want, we can log a message in this case as well, like we did earlier. And let's delete this action montage not valid. Okay, now what we need to do is we need to get a reference to the avatar character and then play a montage on that character. But we have a bit of a problem, and the problem is that we only have access to the avatar actor and not the avatar character. So since we only have access to the avatar actor, which is an actor, we need to convert the avatar actor to a character. And we can do that with something known as a dynamic cast. A dynamic cast safely converts a pointer from a base class to a derived class at runtime, returning null pointer if the conversion fails. It's like checking if a generic vehicle is specifically a car before trying to open its trunk. In our case, an A character is a child of A actor. So that means a character has what is known as an is a relationship with an actor. An is a relationship simply means that one class inherits from another. So a character inherits from an actor. A character is a actor. So that means we can use our avatar actor reference to cast to the avatar character. So to do that, let's create an if statement here. If a character pointer avatar character equals, and we're going to add a cast, which is our dynamic cast with arrows here. And we are going to be casting to type a character. And here in parentheses, and this is going to be the object we are casting to. In this case, get avatar actor. Okay. And as you can see, we are having an issue. That is because our action system component doesn't know what an A character is. We need to add an include. So let's add a hash include. This will be the game framework character.h. And that fixed up that issue. Now we need to return avatar character, arrow operator, play anim montage. Let's pass in all the inputs, montage to play rate, and start section. Okay, and if it makes it this far, we're going to return 0.f because the cast failed. We've done most of what we need to do. Let's wrap a few things up, then compile and test in the editor. One thing we need to do before we compile is let's set canNeverTick to false. Because we know that we will not be using tick in our action system component. Next, let's actually use the DoesSatisfyTagRequirements function, because currently we do not use it, and if we want our tag system to work as intended, then we need to make use of that function. So what we can do is go to ACS action, and here in ACS action in canStartAction, let's first check if action comp is valid, and we are going to return DoesSatisfyTagRequirements, and we're going to get the action comp, dereference the pointer, and get the active gameplay tags member variable from the action component. If it makes it here, we will return false. And you may have noticed some squiggly lines there. It just means we need to hash include action system, and then ACS action system component.h. That should be all we need to do. Let's compile and run the editor. So I'm going to press Ctrl F5. Okay, my build succeeded. If your project didn't compile successfully, you need to keep in mind that C++ code needs to be exactly correct, and any small mistake can cause your code to not compile. I'm going to quickly scroll through my Now that our code has compiled and we are in the editor, let's create an example jump action to test our action system. Now we already created an example jump action. If we open this one up, you can see the action tag is action.type.jump, and that's the only thing we changed. Let's go to our player character blueprint, and here we need to add an action system component, and let's name this one action system component. Next, we need to click on the action system component in our character and go to the details panel. Here we need to find the default actions. We need to add the jump action. Now the default actions in the C++ is this array here that we created in the C++. And if you remember, we take all of the default actions and add them to the available actions array in our action system component. So that means on begin play, as soon as we play, all of these default actions will be made available to our character's action system component, including our jump action, which means this should work. So let's start action by tag. Let's plug this into started. So if you don't have a jump action, you can simply create one in the enhanced input system. And let's call stop action by tag. Fine, completed. So on start action by tag, let's select jump. Same for stop. Now, if we want our character to actually jump when the jump action starts, we can simply add an onActionStart event. If we click the action system component, you'll see we have an onActionStart, onActionStop, onActiveTags updated. Let's add onActionStart. Now, those delegates that I showed you in the blueprint correspond with these delegates here that we set up in the C++. So this is the onActionStart declaration. This is the onActionStop. This is the onActiveActions updated. And another reason why they show up in the blueprint is because we made them blueprint assignable. And if you'll remember, here on start action by tag, we broadcast onActionStart. And same thing for stop action by tag, we broadcast onActionStop here. So these events should fire at the correct time. Let's add a switch statement here. Let's add action.type.jump, and here let's call jump. Copy and paste this. Let's call stop jumping. Okay, let's see if this works. I've pressed the jump button, my character is jumping. Now let's test if our active gameplay tags are working. So what we are going to do is let's go to our jump action. On granted tags, let's add status is falling. And for blocked tags, let's add status dodging. So if you need to create that, just simply add a gameplay tag and do it that way. And also for testing purposes, let's add in the player character, right mouse button, get the action system component. Let's call a function that we created in our action system component called grant active tags. So this is going to grant tags to the action system component, make a literal gameplay tag container, status, dodging. And let's actually do this on a flip-flop. So essentially a flip-flop just alternates between A and B. If we press it once, it will do A. If we press it again, it will do B. So let's clear active tags, plug that in here. So first, let's test by hitting play and searching for the player character. In the outliner, click the player character, click action system, and here in active tags, press the mouse button, the right mouse button, it says status dodging. If I press it again, it removes it. So if status dodging is here and I try to jump, I can't. So that's working correctly. And that is because we added status dodging to the blocked tags for the jump action. If I press right mouse button again, it removes it and I can jump again. So we have confirmed that everything is working correctly. In this video, we're going to implement the action interface, which will give us a sweet spot between modularity and maintainability. We are also going to improve the jump action, make our action system more flexible, and reduce coupling. To achieve our goals, we'll dive into some key programming concepts like inheritance, polymorphism, interfaces, and coupling, and see how they all come together in our flexible action system. Okay, with that out of the way, let's go ahead and get started. We created an example jump action. Since it was just an example to test the action system, we didn't fully implement it. Let's fully implement our jump action by creating a jump action class. In the editor, let's create a new class that inherits from ACS action. So here in public action system, let's create a new class. Here in all classes, let's search for ACS action. Next, and we will put this in public action system actions. Including base class underscore in the name of a child class is a common naming convention in Unreal Engine. So let's follow that convention for our actions by naming our action ACS action underscore jump. And let's create class. You might be wondering why we created our jump action as its own class that inherits from ACS action. To understand that, you must first understand inheritance. Inheritance allows a class to acquire properties and behaviors from another class, creating a parent-child relationship. Our ACS action jump will inherit all the core functionality from ACS action automatically. Think of it as building on top of existing code. You get everything the parent has, plus your own additions. The key benefit is that the jump action inherits all the base action features, so there is no need to rewrite the base action logic. We just need to add jump-specific behavior onto our jump action. We've actually already been taking advantage of this feature in Unreal Engine. The action class inherits from a data asset, while our action component inherits from an actor component. Now that we've taken advantage of inheritance by creating our jump action, let's take advantage of another object-oriented concept known as polymorphism. But to do that, you must first understand what polymorphism is. Polymorphism means many forms, so one class, multiple implementations. Perfect for treating different object types uniformly while preserving their unique behaviors. This allows objects of different classes to be treated as the same type, while each executes their own specific behavior. In our case, inheritance allows each action to inherit the ability to start and stop, while polymorphism allows each type of action to produce different results depending on the action type. The benefit of this is that the action system only needs to use a base action class pointer to point to any derived action class object, and when it calls virtual functions, it automatically calls to correct derived class implementation at runtime. So start action on a jump makes the character jump, while on a dash, it makes the character dash. This works because in our ACS action class, our start action is a virtual function. Without virtual, calling start action through an ACS action pointer would always use the base version. The virtual keyword tells C++, check the actual object type at runtime and call that implementation, enabling the many forms to work. All we need to do to take advantage of this is to override the virtual function start action. That is why we marked this function as well as these other functions as virtual. Let's go ahead and override start action. Here in our jump, we'll just copy and paste that, and then add override here. And after that, let's create a definition. Let's start by just logging to the screen to help us see polymorphism and inheritance in action. So here we can do UE_log temp, warning, text macro, and here in quotes, let's add ACS action underscore jump, scope resolution operator, start action. Okay, and now let's copy this and go to the base action class, go to the CPP file. You can do so by in Visual Studio, holding Control and pressing KO. Here in start action, paste it and remove the underscore jump. Save all and go back into the editor. And let's try using live coding this time. Okay, now in order for this to work, we are going to need to find our jump action and change it to inherit from the jump action data asset, which is easy to do. Here in our actions, jump action, we just need to right click on it, convert to different data asset type. We need to convert it to ACS action jump. Okay, save all, open it up, make sure everything is still set correctly. And also let's go into the character class and let's remove all of this because we are going to be re-implementing that anyway. We can temporarily unplug this while we're testing, so that way this doesn't become a problem. And before we test, let's clear all log messages. And now let's try to jump. And as you can see, it's logging ACS action jump start action. it only outputs the jump actions version to the output log, but we don't lose the parent functionality by doing this. We can still call the parent version of the start action function. So while keeping the editor open, let's go to the jump action function and call super on it. Calling super like this: super scope resolution operator start action, passing in action comp. What super will do is call the parent version of this function. In our case, when calling the jump action, we'll call the parent version of the start action function first, and then our jump action specific logic beneath it. So here in the editor, let's start live coding. Let's test again, and keep in mind that if this doesn't work for you, then you can always close the editor and compile and build from your IDE. As you can see, the parent ACS action and child ACS action jump are both being called because both are being logged to the output log. This is inheritance and polymorphism in action. If we were to, for example, comment this out and comment this out as well, so for some reason it's not working correctly for me when I live code, I'm just going to have to build from the editor. Live coding can be hit or miss sometimes. And as you can see, nothing prints. But if I add the super back and only the super, then I try to jump, it only prints the parent version. Now that we've seen those concepts in action, we can remove those UE logs. Let's go ahead and remove them now. Next, let's implement our jump actions version of the start action function so that we can actually implement the jump action. So remember to close the editor. First, let's call super because we might need it later. Okay, next, let's try to play the action montage, but only if it is valid. Action montage.is montage valid. And we also need to check and action comp. Okay, now action comp, arrow operator, play action montage, action montage. We need to add the include so that we can use the action component. So hash include action system ACS action component.h. Okay, now we need to, from our action montage, access the actual action montage. And then you can see the inputs we have here. Next is the play rate, action montage, play rate. And next is a start section. So action montage, get montage section name. And we need to pass in an index. Let's just put 0 for that. And that's all we need to do. Okay, so what we can do here actually is, let's wrap this in an if statement, action comp, and remove that here. Okay, next, if a character, pointer, avatar character equals, let's cast to a character. And inside these parentheses, let's, from the action comp, let's get the avatar actor. Now, since we are using the a character, we need to add an include for that. So here at the top, let's add hash include a framework slash character.h. Okay, and now let's get the avatar character, arrow operator, let's call jump. Okay, now let's do something similar with stop action. So let's go to the action class and let's copy this one. Let's override it here in our jump action class. Create definition. Okay, and copy this. Remove play montage. And instead of jump, let's do stop jumping. Okay, and I'm noticing a mistake that we made here that we need to fix before we compile. And as you can see, we're checking if a montage is valid and only doing this if the montage is valid. Let's remove this. So that way we only play the montage if the montage is valid. And if it's not valid, we continue and jump like normal anyway. Let's also fix the stop action function. So we check if the montage is valid here. We actually don't need to do that. Now that should be all we need to do. Make sure your code is correct and the editor is closed. Now let's compile and run the editor. Okay, mine compiled successfully. Okay, now let's test in the game. And as you can see, jump is working. Next, let's work on the action interfaces. There are many ways we can implement our action interface. For this action system, we are going to use a grouped approach. More specifically, we are going to group related actions into multiple interfaces. The iCombat actions interface will have functions for things like attack, block, parry, and more, while the iMovement actions interface will have actions such as dodge, dash, and more. That will also allow us to later add other grouped actions such as iInventory actions. This grouped approach will give us a sweet spot between modularity and maintainability. Okay, with that out of the way, let's go ahead and get started. Let's go ahead and create it. So here in Actions, let's create a new C++ class. And here under Common Classes, we should find Unreal Interface. If you don't know what an interface is, an interface allows multiple dissimilar classes to implement a common set of functions. This is useful when classes need shared functionality, but have no common parent other than the base UObject. In this case, an Unreal interface can enforce multiple objects to implement the necessary functions. You can think of it as a skill certification. Any object can be damageable or interactable without needing to inherit from the same parent. Interfaces can also help reduce coupling because you can call interface functions instead of needing to cast to some specific class. That's going to be the primary benefit for our action system. So with Unreal Interface selected, select Next. Let's name this ACS Movement Actions. And let's create the class. Okay, now that you have created the Movement Actions interface, go ahead and close the editor. Now let's define the jump functions in our Movement Actions interface. Since the default character class has its own jump functions, we need to make sure there are no naming conflicts. Let's call the first one Start Jump Action. Void Start Jump Action. And the next one will be Void Stop Jump Action. Now, in order to make this more flexible, let's allow C++ base implementation plus Blueprint override. And to do that, we need to make these into Blueprint native events. So let's add U function. We need to make this a Blueprint native event. And let's make this Blueprint callable. Category will be actions. And let's do the same thing for this one. Now let's implement the interface in the character class. If you don't have a C++ character class, you can simply create one, similar to how we created all of our other C++ classes, except this time just select character. I already have a C++ character class, go to ACS hero character. This has some basic default functionality just for camera and movement input. So this is similar to the C++ default third-person template. You can just create one of those if you want to get a reference to what I have here. But now let's implement the interface. But you might be wondering, how do you implement an interface in C++? Well, C++ supports multiple inheritance, which means a class can inherit from multiple classes. Unreal Engine only supports multiple inheritance through interfaces. So that's how we can implement the interface in C++, simply by taking advantage of multiple inheritance and inheriting from the interface. Public IACS movement actions. And we are going to need to include it before it works. #include system actions, and this should be ACS movement actions.h. Okay, and that has that fixed. Okay, now we need to implement the interface functions. So let's go back to our movement actions interface and copy both of these. Here under the public, let's paste them, but remove this. And for blueprint native events, we actually need to add an underscore implementation to these. I'm going to go ahead and copy that and add it to the one below it as well. And now we need to do override, because we need to override those functions. The underscore implementation version is the core C++ version of our function and gets automatically generated for us when we declare a function as a blueprint native event. Okay, now let's create definitions for these. Now we can do, let's do a UE log first. Ulog log temp warning text macro start jump. And let's do the same thing. Stop jump. Okay, so now let's go back to our jump action here. After that, let's update our jump action to call our interface functions. Since we are allowing blueprint use of this interface, we need to call our interface functions in specific ways. Okay, so let's delete this old code here and let's create an aActor pointer and let's call it avatar actor and have that be equal to action comp get avatar actor. We can wrap that in an if. And in here, we can check if avatar actor arrow operator implements arrows, parentheses, implements UACS movement actions. We need to include it here. So hash include action system / actions / ACS movement actions. Okay, and if that is true, ACS movement actions, scope resolution operator, execute jump action in parentheses, pass in the actor reference we are calling this on, just avatar actor, and that should be all we need to pass for this one. Okay, now let's do the same thing for stop action. Copy, we're in stop action, let's remove this and paste this here. Okay, that should be all we need to do. Let's compile and test in the editor. So make sure you have the editor closed and make sure that your code is correct before compiling. Okay, mine compiled successfully. Before we test, we need to make sure our hero character inherits from our C++ class. Mine inherits from ACS hero character, which is the C++ character class that I'm using. If not, then we need to set our blueprint character to inherit from our C++ character. Go to class settings and find your C++ character here and select that as the parent class. That should be everything we need to do. Let's go ahead and test it out. And as you can see, print start jump for both, but okay, so in our C++ for stop jump, we forgot to change this to stop jump action. Let's try live coding and see if that works. Live coding can be a little hit or miss. Hopefully that was able to fix it for us. Okay, and that works. We have start jump and stop jump. Okay, now what we can do is we can actually implement this in the blueprint. So event start jump action and event stop jump action. So if we implement this into the blueprint, since this is a blueprint native event, so I can go ahead and print string blueprint start jump action and blueprint stop jump action. Let's go ahead and try again. And you can see it prints to the screen. And in the output log, we no longer see the C++ version being called. And that is because the C++ version is not being called anymore. If we want to call the C++ version, we'll have to call super on these functions, similar to how we did earlier in the C++. In Blueprint, you simply need to right-click, add call to parent. So this is equivalent to calling super. We do that for both of these. We should get both in the output log. And as you can see, we get both. exactly as we are supposed to. We can call the C++ implementation in addition to the blueprint implementation, or we can completely override them if we don't call the parent version. So for example, we can add jump here, and we can add stop jumping here. Let's test. Nothing gets printed or shown in the output log, but jump now works. You can leave these in the blueprint if you want to, but I'm going to implement these in the C++. Back here in the C++, let's go to the hero character. Let's remove these UE logs. And for start jumping, let's call jump. And for stop jump action, stop jumping. Okay, let's go ahead and fire off live coding and see if it works. If not, we'll have to close the editor and compile manually. Okay, that's working. Modifying our jump action to use an interface instead of a cast actually made a positive change to our code by reducing coupling. If you don't know what coupling is, coupling measures how much one class or module depends on another. Low coupling means classes are independent and flexible. High coupling means they are tightly interconnected and hard to change. Previously, our jump action required the avatar actor to be a character so that we can cast to the character class and call the character jump functions. But now we are using the movement actions interface for that. So this character include is not needed anymore. Our jump action is now more flexible because it is no longer coupled with the character class. We can now, for example, use the jump action with a pawn if we wanted to. This video has become quite long, so I think this is a good place to end it. In this video, we learned about inheritance and polymorphism and how we can use those concepts to treat different action types uniformly while preserving their unique behaviors. We also made use of interfaces, which allowed us to improve the flexibility and reduce coupling. In this video, we are going to do some refactoring and improve the flexibility of our action system. To achieve our goals, we'll dive into some key programming concepts like refactoring, object pooling, and context data, and see how they all come together in our flexible action system. Okay, with that out of the way, let's go ahead and get started. Let's start by doing a bit of refactoring. But what is refactoring? In software engineering, refactoring is the process of restructuring existing code without changing its external behavior. The main goal of refactoring is to improve the internal structure and readability of the code, making it cleaner, more maintainable, and easier to extend, while ensuring that the program still does exactly the same thing from the user's perspective. The first thing we are going to refactor is the action class. We are going to change from using a UDataAsset to a UObject. The reason for this is due to the limitations of data assets, which limits the flexibility of our action system. UDataAsset in Unreal Engine is specifically designed to be used as configuration or reference data that shouldn't change during gameplay, meaning they are primarily designed to store static, read-only data that should not be modified while the game is running. Technically, it is possible to modify properties inside a data asset at runtime, but Epic discourages that. The reason for this comes down to how Unreal Engine's memory management and garbage collection systems treat UDataAssets based on their intended purpose and lifecycle. To put it simply, data assets are designed to be shared reference data, and the engine treats them as such. Meanwhile, UObjects are treated as instance per owner, so they are per instance state, which means that they can represent almost anything: gameplay logic, runtime state, temporary data, assets, and more. The reason why I initially opted to go for a data asset despite its limitations is because using a UObject will require us to manually create a new instance of the action object before we can call its members. We also need to worry about optimizing so that we avoid creating too many instances, which is a bit more complex versus data assets where the engine handled that for us. But I think we've covered enough topics, so you should be ready for it now. So let's reparent the base action class to a UObject instead of a UDataAsset. So let's go to the ACS action header file here, and let's reparent from UDataAsset to UObject. And up here at the top, let's replace this include with UObject/no export types.h. Now we need to go to the UACS action system component and modify our logic to create a new instance of an action before trying to use it. Because as I was saying earlier, with UObject, if we want a valid object to access, we need to create an instance manually. So let's go to the ACS action system component. So in order to create an instance of an action, we will need to know what class to use, because we don't want to be creating instances of the parent class. The reason for that is because the parent class has nothing in it and is designed to be overridden in child classes. So that means we are going to need to know the class to use when creating our instance. So let's create a start and stop action by class. Let's copy these, paste them below, and instead of by tag, these will be by class. And instead of the action tag, let's do t sub class of arrows ACS action. Actually, it'll be UACS action. And this will be the action class. The reason why we are using t subclass of is because t subclass of is a template class used to hold a reference to a U class type while being safely restricted to subclasses of a specific type. This will provide type safety for our action system by only allowing us to select a class that's a subclass of an action, because we want to restrict the action system to use the action class. So let's do the same thing for stop action. Now let's create definition for both of these. So for these, we can just copy and paste from the other ones, but make sure that you copy stop correctly for stop. So let's copy this coming from stop action and paste this into stop action by class and copy start action by tag. And we just need this bit here, not the whole thing, and paste that from start action by tag into start action by class. Okay, now we need to create our action object instance. So let's go ahead and do that. So this will be UACS action pointer. Let's call it action. Make that equal. Now this is where we need to create our instance for our action object. In Unreal Engine, you need to create a new object instance with new object. So it goes like this, new object. And we need to specify the type. So add those arrows and then UACS action. We are also going to pass in a few inputs like the outer, which is going to be this. So we are passing in the action system component as the outer, and then we can pass in the class as well. So that will be action class and then semicolon. Now we can modify this a bit. So what we can do is cut this from here and remove this, and then remove this part here and paste that here. And this will work because in C++, it will check the left first, and if that fails, it will not check the right. Even if action is not valid, this will not cause a crash. And for the action tag that we are trying to get here, we can simply get it from the action, like that. Okay, now let's do something similar for this one. Let's compile and run the editor and see if this works. Okay, mine compiled successfully. Okay, now that we are in the editor, let's go fix the jump action because it is likely going to be broken due to reparenting the base action class. Blueprints actions, jump action. Okay, I can't delete it because it's referenced here. I think we added it here. Yes, we did. Now we should be able to delete it. Let's see if we can create a jump action. Looks like we can't. So close the editor. And so we need to make the action blueprintable. And to do that, we can go inside the U class here and just add blueprintable. Now let's build and run the editor. Okay, now let's try again. Search for jump, and now it shows up. select that, and let's call this B for blueprint underscore jump. Let's open this up. If we close it and open it again, it will show us this data only view. And we can go ahead and add the action type jump. For the granted tags, I believe we had status falling. And for the blocked tags, status dodging. Okay, now let's go here in our hero character and let's call start action by class. So instead of running that one, let's run this one. And we can do that easily by holding control and then dragging like that. Stop action by class. Let's use the jump for the class. Okay, and before we test, make sure you unplug this, just in case you accidentally press this and it doesn't work. Okay, and now it's working. But even though it's working, we have a problem. So if I jump several times like this and keep jumping over and over, and then move this to the side, and then go to the jump action object and open full blueprint editor, there is actually a way of looking at how many instances of an object has been created. So you can select that here. And this shows us all the instances of the jump object that have been created. So if I bring this back and jump a lot more, then move this away again, you can see that we have even more created. This is because each time we jump, it creates a new instance. Not only is this inefficient, but since we have no way of accessing the instance object again, the objects will eventually be garbage collected by the engine, so this won't even fix our initial problem. In order to fix this, we need to use a practice known as object pooling to hold on to and reuse the object instances we create. Object pooling is the practice of creating a pool of objects to access and reuse later instead of constantly creating and destroying them. This improves performance and efficiency by avoiding unnecessary memory allocation during gameplay. You can think of it like reusable dishes. Reusable dishes stay in the cabinet and get cleaned for reuse later, while paper plates need to be constantly thrown out and replaced with new ones. The simplest way to create a pool of objects is to store them in an array, which is what we are going to do in this action system. We actually already created an array of objects. We created the available actions array, and this does as the name suggests, it just stores the available actions in an array. So we can simply reuse this as the object pool for our actions. And we can do that by modifying the giveAction function here. So giveAction. And this is where we are going to create our action instance. So when we give an action, we are going to create the instance and then store that instance in the available actions array for use later. This will act as our object pool. So let's go here to start action by class and copy this line where we are creating the new instance for the action and paste that here. And for give action, let's change this. So let's copy this input here. And for give action, let's paste that here. Update the one in the header file. Okay, and action class not valid. Let's name this new action. Okay, so now we are creating an instance of an action, and we are using the action class that we provide in the input to the giveAction function, and then we are setting the result of that to new action, and then adding that to the available actions. Okay, now we need to update the default actions, because as you can see, there's an error now. So what we need to do is go to our default actions array, and make this into an array of t subclass of. Subclass of UACS action. Okay, there we go. P subclass of UACS action. Okay, there we go. Okay, now let's go down to start action by class. And now we should be able to do something very similar to what we did in start action by tag. So let's copy that and let's remove what we have here and paste it. Okay, so instead of trying to check if the tags match, let's check it class is equal to action class. And let's copy this and paste it here. And now let's do the same thing for stop action. Class and class. Okay, that should be all we need to do. Because we did do a lot of the heavy lifting already, we really just needed to modify what we already had so that it stores our action instances instead. So now let's compile and run the editor and see if it works. And make sure you have the editor closed so that way it compiles successfully. Mine compiled successfully. Now let's open full blueprint editor again for the jump. And now let's start jumping and see what happens. Okay, so it's not working because we forgot to actually give the action. If you remember, the only time we instance the action is when we give the action. So if we don't give the action, then that means that there is no valid instance of the action. So we can either manually call give action, or we can use within the action system component the default actions. So let's add bjump and see if it works. Okay, and now it's working. So let's jump a bunch of times. Okay, now let's move this out of the way. And as you can see, only one is created now. So our object pool is working correctly. And this also means that start action by tag should work as well. And the reason for that is because we've set the tag here and we've already given the action to the default actions. So the action is given to the available actions by default on begin play. And now when start action by tag searches the available actions, it should be there and it should work. So let's go ahead and try that. And it does work. There is one more thing that we forgot to fix. So we do have give action where we can set a class to give, but for clear action, it's still set to an object reference, which we don't have anything for that. We have no way to get the action so that we can clear it. So what we're going to do is close the editor and let's go to the action system component header here. And let's copy the T subclass of here and paste it here for clear action. Let's go to the CPP file and do that here as well. Okay, and now we need to check is not action class. So is the action class not valid? Action class not valid. Since we're working with a class now instead of a direct object reference, we are going to need to remove the action from the available actions array a little bit differently. So one way that we could do it actually would be a for loop for UACS action pointer action available actions. Then check if action and action get class is equal to action class. If that's the case, then we can call remove. We could do it this way, but we're actually not going to do it this way. I just wanted to show you that we could do it this way. Now, the reason why we are not going to do this is because it is not a good idea to remove from an array while you are looping through it. This is because of how arrays shift when you remove elements, which could lead to skipping elements. And that's something that we don't want. We don't want the array shifting to cause our for loop to skip elements because we need to loop through and find the classes that we need to remove. So what we can do is use a reverse for each loop. This is how you do a standard reverse for loop. So for, let's declare an int 32, I equals, and then we're going to have available actions dot num -1, which gives us the last element. I greater than or equal 0, and then minus minus I. Okay, and now we can just do the same thing, except instead of action, let's do available actions, and to access an array element, use brackets, and I is a current index in the loop. If that is valid, let's remove that and then replace it with this. So this just gets the action at the current element in the loop. Then we are going to remove it. Now the reason why this fixes our problem is because when going backwards, removing an element only affects indices after your current position. Since it is a reverse for loop, it's moving left, so it never revisits or skips anything. And before we compile and test, it looks like we made a mistake here. So instead of remove here, we should actually use remove at. And we remove at I. And also something else that I wanted to add is if you're confused by the syntax of this for loop, then let me explain that to you before we compile and test. The syntax used for our reverse for loop is pretty standard C++ syntax. In fact, if you take an introduction to C++ class, that's probably the kind of syntax they'll teach you. While it may look pretty confusing if you're new to it, the syntax is actually pretty simple. So let me add a comment here for, and the parentheses, and inside the parentheses we have initialization, condition, and update. And so that's how it works inside the parentheses here. So for the initialization, this runs once at the beginning. Condition, if true, the loop runs. If false, the loop stops. For update, this runs after each iteration of the loop body. And so that's how this syntax works. And this particular for loop is iterating backwards through our available actions array, starting from the last element and going down to index 0. Now let's compile and test. Okay, now let's test. Calling clear action. Let's clear the jump. Okay, if I don't press right mouse button and I jump like normal. But if I press right mouse button and try to jump, I can no longer jump. That's because the jump has been cleared from the array. So it works just fine. In this video, we are going to continue refactoring and improving the code and flexibility of our action system. To achieve our goals, we'll dive into some key programming concepts like refactoring, context data, and the single responsibility principle. Okay, with that out of the way, let's go ahead and get started. Now, speaking of making our action system more flexible, let's use what we've learned to improve the flexibility even further by replacing the avatar actor functionality with context data. But what is context data and how do we use it? Context data is data that provides additional information about the circumstances in which something is happening. A kind of snapshot of the current logic context used to make a decision, perform a calculation, or execute behavior. Passing context data containing generic base class pointers through a function and casting to what you need in derived classes separates logic from context, allowing for flexible and modular gameplay systems. In this action system, we are going to use context data as context containers. This data will let our action subsystem operate without having to look up or guess what objects it should interact with. So let's go ahead and make the struct. Let's go to the action, and here at the top, let's add a uStruct, print type, struct, ACS action context. Let's add the generated body. Here we can add our U properties. So what are we going to include? Well, we can include some base classes that we think our actions will use. Things like the avatar actor, avatar character, anim instance, maybe the avatar mesh, and any other generic base class that we might need for actions. Property. tObject PTR, a actor. This will be the avatar actor. Copy and paste this. Let's delete that. Make this an a character. We might want to add class in front of these before we declare them. Our character. Add another one. This will be class U skeletal mesh. This will be avatar mesh. And then this one will be class U anim instance. The avatar anim instance. And I guess at the top, it's also just a U object, context object. So this will be just a generic context object. Okay, now what we can do is go to our action system component. We are actually going to, here in the header, you're going to need to include #include ACS action.h. Okay, here in the action system component, make this a private variable, property, if ACS action context. And now we can remove avatar actor from here. What we can do is action context dot avatar actor. So we're setting that instead. Forget avatar actor. I think we have some functionality for that here. We can actually just remove this entirely because we're going to be doing this a little bit differently now. Let's remove this getter function. Let's create setter functions for the other ones as well. So just copy and paste this a few more times. Let's change the top one here to UObject. Context object set context object string context object context object. Let's have this one be the avatar character and character. Actually, since we're naming this in actor in character, let's also do this one as in object. And avatar character is going to equal in character. Let's rename this one to set avatar character. I have it set as an a actor right now. We need to make this an a character. Now we need to set avatar mesh. U skeletal mesh pointer in mesh avatar mesh equal to in mesh. Okay, now let's paste this one more time. And this one will be set avatar anim instance U anim instance in anim instance avatar anim instance equals in anim instance. The next thing that we should do is let's implement a way to pass the context data through these functions here. So instead of the action component, let's pass the context data. So let's add if ACS action context, call it action context, and let's make this a const reference. So that way we are passing a safe reference and not a copy. And since we made this reference const, it cannot be modified, so it's safe, which is good practice to do. Let's go ahead and replace that for all of these. Okay, now let's paste them here. But you will see that we do need the action component in some places. So to fix that, what we can do is something simple. Let's just do ACS action system component pointer get action system component. Let's make this const. So let's also expose this to blueprint. Blueprint callable category equals. Okay, and now let's create definition. Here we can cast to UACS action system component. We can use the get outer, and this will work because if we go back to our action system component, when we are creating the action instance object, we are passing the component as the outer object. Let's go back here and we can replace this with get action system component. Or we can actually just make this get action component a little bit cleaner. We can set that as a local UACS action system component pointer action comp equals get action component. And now it works. Now let's fix the jump action. Here we have this copied. To paste that here. Okay, we need to pass the action context instead. Okay, and as for the action component, do something similar to what we did before. UACS action system component pointer action comp is equal to get action component. Okay, so this function no longer exists in the action system component. What we can do is we can simply get that from the action context. Action context, avatar actor. Okay, and we can do the same thing here. And since we don't use the action component here anymore, we can actually remove this check. Okay, now we have the context data implemented, but we don't actually set this context data with any valid objects. So when trying to use the context data, nothing is going to work. So what we need to do is we need to go to our action system component, and here on begin play, first let's set the avatar actor. So if a actor pointer avatar actor equals get owner. So we will set the avatar actor as the owner. So now let's call set avatar actor, and we will pass in avatar actor as the new avatar actor. We need another if a character pointer avatar character is equal to cast. We are going to cast to a character. The target for the cast is going to be action context avatar actor. Now let's set avatar character. This will be the avatar character. Next, let's set avatar mesh. This will be avatar character get mesh. Okay, it looks like we have an error. Oh, okay, I see what we did. We go here to our action class. It looks like we made this a skeletal mesh instead of a skeletal mesh component. Now we need to update the function here, use skeletal mesh component. Now let's set avatar anim instance. And this will be action context mesh, and from here we can call get anim instance. Okay, let's go check to see if there's anything else we missed. Looks like we missed this. So what we need to do is pass the action context here. We should be ready to compile now, but since we did a lot of refactoring, I'm going to go ahead and scroll through my classes. So that way, just in case yours doesn't work, you can reference what I have here. Okay, now time to compile and run. Okay, now I'm back in the editor. I'm going to go ahead and test, and jump is still working. I'm also going to test this as well. And that seems to be working as well. Next, let's make our code cleaner by extracting code into separate functions. In a previous video, I talked about the single responsibility principle, where a software component should focus on a single well-defined responsibility or role. That also applies to functions as well. By extracting code into smaller functions, each with a well-defined role and a descriptive function name. This creates code that reads like a clear outline rather than a tangle of implementation details, keeping high-level concepts at the top, descending in detail as you go deeper. This technique dramatically improves readability, making bugs easier to find, simplifies testing, and makes onboarding new developers much faster. It's one of the most widely taught and respected practices in modern professional software development. Let's start by extracting a lot of this code from BeginPlay into their own functions. To do that, let's extract this code here. So what we can do is right-click and quick actions and refactorings, extract function, and this will be a member function, and it will be below current function. And we can call this one initialize action context data. Now let's do the same thing for the code that gives the default actions to the action system. Except for this one, call this one give actions. And let's change this one slightly. So remove that from here, and let's put it underneath give action. And let's copy this as well. Let's pass in a T array, and this will be T subclass of, make this a reference, action classes. Now let's go copy it here. Okay, and let's cut this and paste it below give action. Okay, now let's remove default actions and pass in action classes. Okay, and now we can add default actions into here. So instead of all of that code being in the BeginPlay function and having to look through all of that code to figure out what it is doing, we can simply look at the names, initialize action context data, and give actions, and we can know exactly what they are doing without having to worry about the details of the implementation. So this, as I was saying earlier, reads like a clear narrative rather than a tangle of details. The clear narrative in this case is we are initializing the context data and giving the default actions. Let's also create a clear actions function just in case we need it. Copy and paste this, and copy and paste this here. Clear actions. And let's copy this. Instead of give action, we can call clear action. Okay, now let's go to the action class. Let's do some refactoring in the action class to make the code a bit cleaner. Now let's start by going to the jump action and extracting the play montage code into its own function. So let's go ahead and do that. Play action montage. Let's move this code to the parent so that all actions can benefit from this function. Okay, let's remove jump from here. Okay, and we can go to the action system component here and find play action montage and copy the inputs and paste them here. Okay, and what we can do is we can take this out. We can make this into an early return. Before we do that, let's make sure we are returning a float. Let's return 0.f here. And we need to make this a not, so that way it only returns if action montage is not valid. Let's add if UACS action system component pointer action comp equals get action component. And we already include the action system component, so we're okay there. Now we can go back to the jump action. We can pass action montage, play rate, and action montage get montage section name. And now we can remove this check from here, and it's a little bit cleaner now. Okay, so I tried to compile, but there were some build errors, so it looks like we made a few mistakes. The first mistake that we made is we forgot to return a value here. In C++, all control paths must return a value. So let's return 0.f here. We also forgot to remove this, which counts as a redefinition. We can comment this out by holding Control-Shift/. Same for this one. We also made another mistake where we meant to pass through these inputs into this function, but we ended up not doing that by mistake. So let's pass montage to play rate, and start section. And we also need to return the value here as well. So return, which will return the value that is returned by this function from the action component. Okay, I'm going to try to compile and run the project, but before I do that, since we've refactored so much and made so many changes, I'm going to scroll through all of my classes so that you can reference my code in case you made some mistake. Okay, now let's go ahead and compile and run the editor. Okay, mine compiled successfully. Next, let's continue refactoring the action class to make the code a bit cleaner. We are going to do that by first extracting our structs, facs action context and f action montage, into a separate header file called acs action types. So why use a separate types header file? Right now, these structs are defined inside the acs action header file. This means any class that needs these structs, like our action system component for example, must include the entire action class header just to use a simple struct. By moving them to a separate header file, we get two key benefits. The first is cleaner dependencies. Classes can include just the lightweight types header instead of the full action class. So if the component only needs facs action context, you only need to include just the types and not the entire action implementation. This will also prevent circular dependency issues as the system grows. The second benefit is that it keeps our action class header focused on the actual implementation, making the code easier to read and maintain. This is the same pattern Epic uses in the engine code and for systems like gameplay abilities. It's a simple practice that makes larger systems much more manageable, which is why we are going to take advantage of this practice. So let's go ahead and create our types header by creating a UObject class within the editor. So let's go to Actions, New C++ class. This will be an object. And let's name this one ACS Action Types. Let's create class. And we can close some of these out. And now we can go to ACS Action. Let's copy these over. And now that I'm looking at this a little more closely, it seems like we forgot to add ACS here, like we did for this one. And I would actually like to rename this to just montage. Now let's go to ACS action. Let's include actions, ACS action types. And we need to make this facs action montage. We also should open up the jump action again. We need to change this to montage. Okay, now we can close it again. And next, let's go to the action system component here. We can actually replace this with actions, ACS action types. The reason why we no longer need to include ACS action and we can replace that with ACS action types is because the only thing the action component header was using from the action class is the action context data struct. So down here, this is the only thing that we were using from that class. And since we put this struct in a separate header, we now only need to include the types header for that file, which is much cleaner because we no longer need to include our entire action class in our action component just to use one struct. We are going to finish up the action system by implementing some example actions and cover how to handle action blocking and canceling. But before we add actions and implement action canceling, we need to expose our code to Blueprint so that we can use Blueprint and C++ together. This mirrors how a lot of professional development actually works. You can see this in examples like Valley of the Ancient or Lyra project, where a lot of the core bits stay in C++ while the gameplay extension layer is exposed to Blueprint. And in order to achieve that, what we're going to do is go to these functions here. Let's make them EU function. This will be Blueprint native event. To explain why we are using Blueprint native event, a Blueprint native event is basically a U function specifier that allows a function to be defined in C++, providing a default base implementation while also being overridable in Blueprint. So it's an option that allows you to use Blueprint and C++ together. And just give this a category that equal to action. And we can do that for almost all of these, like this. Now, the way Blueprint native event actually works is the C++ implementation has to have a underscore implementation. Let's go ahead and copy that. Okay, and we also need to copy this as well for play action montage, except this will be Blueprint callable. And Blueprint native event requires this to be non-virtual. Go ahead and remove that. And before we compile, we need to fix our C++ action. I believe the only one we have is jump. And go underscore implementation underscore implementation. Let's go to the C++ and add that here. And one more thing we need to fix before we compile is we need to add underscore implementation here to the supercall, because we always only want to do the supercall to the C++ version in C++. If you try to do a supercall to the regular version like this, then it will cause a crash. So just keep that in mind. Okay, everything looks correct. Now let's compile. Okay, now let's check the jump asset, which I renamed to BP underscore jump. Everything looks correct here. And if I open up the hero character and check, it is added to the default actions. So as you can see, it still works. Okay, now let's create our dodge and attack actions. So let's search up action, ACS action. And if yours doesn't show up, just to make sure that in the base action class, it is blueprintable. Okay, and now this is going to be BP underscore hero underscore attack. And let's duplicate this, hero underscore dodge. Okay, and for the dodge action, let's add action tag, action type. Let's add a subtag, dodge. Okay, and granted tags, let's add status, dodging. And if you don't have that, just add it. Okay, now we need to set the action montage. Now I already have a montage for that. Create a montage and select that here. And for attack, make this action type normal attack. And again, if you don't have that, you can simply create it. And for the attack primary A will be fine. Okay, and granted tags will be status, attacking. Okay, now let's do something very simple. Let's just add a left mouse button for testing. Now you would want to do a proper enhanced input action for this, but since this is just a test, then this will be just fine. You're going to start action by tag, action type, normal attack, and then do left shift, start action by tag, dodge. And now we need to grant both of them. Here in the component details, we need to add hero attack and hero dodge. Okay, and now we need to go into hero attack, open a full blueprint editor, override start action. Let's play action montage. Now let's see, get action montage. Let's break that. Okay, so it looks like we can't break this or get the values from it. Let's close the engine, go back into the C++, and let's find where we have that at. The action types. There's action context, action montage. And here, let's try to make this blueprint read write for all of these. Now let's compile and open the editor again. Okay, now we should be able to break, and here we go. Plug that in, that. Let's do a simple get here. Okay, and let's do the same thing for dodge. Let's override start action, play action montage. Okay, now let's test to see if it works. Okay, so it looks like attack is working, but dodge isn't. And the reason why dodge isn't working is probably due to the animation. So this is the default slot. Let's just go to the animation blueprint. And here where it says full body, let's just add the slot, default slot. And put that right here. Now I might also need copy and paste this and do the second one as full body. Okay. And now that works, except I need to enable the root motion. So let's open asset and search for root motion, enable root motion. Okay, there we go. Now you can see we're having cancel issues. Let's go ahead and work on that. And the way we are going to fix that is by going to our dodge and adding blocked status, dodging. Do the same thing for attack, attacking. Now let's see what happens. So now we can perform it once, but we can never perform it again. How do we solve that? Well, let's check in the C++ if we've created anything. It's like we haven't. That's okay. We actually don't need to do that in C++. We could do it in C++. Maybe that's something we'll do later. But for now, let's keep it in Blueprint. Let's create a Blueprint class. Let's add an anim notify. Let's call it an underscore stop action by tag. Now let's override receive notify. And from the mesh component, let's get owner, get component by class. And here we get the action system component. If it is valid, then let's call stop action by tag. And let's promote this to a variable and expose it. And now let's open up the animation for dodge. And here at the end, when we want the action to be considered over, set notify, stop action by tag. And this is going to be the dodge action. And the same for attack. Okay, action tag, type, normal attack. And as you can see, it works now. However, you may have noticed that this created a bug. So if we spam attack like this, it works just fine. However, if we attack in the middle and cancel out, now we can no longer attack. This happens because, as you can see here in the animation, stopping the action happens near the end. But if we cancel before that happens, then this will never run. Now we will implement a proper solution to this here in a second, but for now, we are just going to do a very simple solution. And that is, during attack, we're going to block dodging. And during dodge, you're going to block attacking. Now that no longer becomes a problem, but we definitely don't want that to be the final implementation because we want to implement support for canceling out of actions early. But we will do that later. For now, let's work on the next problem, which is we can attack while jumping and dodge while jumping. Now it's actually very easy to fix this. So what we can do is go to the hero attack, blocked tags, is falling, same for the dodge, is falling. Now this won't work just yet. We actually need to apply that tag. And the best way to do that is event on, I think it's called event on movement mode change. So what we're going to do here is we are going to add gameplay tags to the action system component based on the changes to the movement mode. So let's create a function, update movement mode tags. And what we're going to do is we're going to add an input, the movement mode. Let's create another one. This will be previous movement mode. And this will be new movement mode. What we're going to need to do is clear active tags and grant active tags. And how we're going to do this is let's create a new variable. This will be of type e movement mode. And we will make this into a map. And the second one will be gameplay tag container. Movement mode tags. Okay, and let's make this into the category movement. Okay, and let's add a new entry here. The only one we need to worry about right now is falling. So select that. Status is falling. Now, if you want to, you can add all of the ones for the other ones, but we are not going to need that. So I'm just going to add falling. We can also create a getter function if we want to. Get movement mode tags. This will be movement mode. This will return find movement mode and return it. And this will be both pure and const. Now, so we can actually get the local variable by typing get prev movement mode. And what this will do is just get the local variable here. So this is the same thing as just doing this. It just looks cleaner. Do it this way. Let's do the same thing for the other one. But we don't need the previous movement mode. We need the new movement mode. Okay, now let's go ahead and call this here. Previous to previous and new to new. Okay, now let's see if it works. Okay, so for some reason it's not working. And I think I know why. And that's because on jump, we have granted tags is falling. So we need to remove that. And the reason why is because we go here to our hero Greystone and the jump action, we can see that when the input is completed, we stop the action, which will clear the granted tags early. meaning since we had is falling here, that would clear the tags early, which is not what we want. We want the is falling status to only be controlled here. And also if you have any testing like this, just delete that because we don't want to create issues. And it looks like that fixed it. Yep. And it should even work whenever we fall off, since we're using on movement mode change. Yes, it does. Okay, next let's add support for action canceling. So we want to be able to dodge during attack. So let's go to the hero dodge and let's remove attacking. So that way we can dodge while attacking. But that issue is back now where we can no longer attack if we canceled early. And as I explained before, the reason why that's happening is because we only stop the action here near the end of the animation. So if canceling happens before this, so at any point between here and here, then this never calls and this attack action never stops. Now, one way that we could solve that is here in the dodge action, we can just stop the attack action. But that would require manual work. It would be nice if we could have this to be more automatic. So that way we're not creating issues for ourselves later. And the way we are going to do that is by taking influence from the animation montage system. So the animation montage system is something known as the current montage. So we can do get current montage. And if we read the comment for this, it says it returns the current playing montage. So we can use something similar for our action system. Let's go ahead and save everything and close the editor. And let's create an implementation of a current action. So here in the action system component, let's go ahead and create the current action. We can do it right below the active actions. This will be a P object PTR, UACS action, current action. And here below, add active action and clear active action. Let's create some view functions here. Void set current action. And what we're going to do here is simply set the current action to equal new action. And we can do the same thing for clear as well. We won't need this. This will be clear current action. And this will simply set the current action equal to null pointer. Okay, next let's create a function to stop the current action. And we can create it right here. Let's just copy and paste this. We'll stop current action. And we can also create a getter function. Copy this. Let's return UACS action. Pointer get current action. Make that const. This will simply return current action. Okay, now let's create this into a function to stop current action. And what we need to do here is we need to check if current action is valid and active actions contains current action. If those are true, then we can check something similar to what we did here. Current action. Instead of continue, we can return. It cannot be stopped. And then we can also do some similar things as well to that one. Right here. Current action, handle action stop, current action. Okay, and next, let's go to handle action stop. And here on clear active action, let's open that up. Let's add another condition here. If action to remove is equal to current action, we set current action to null pointer. Okay, now let's go create some helper functions within the action class. So here below stop action, let's create a blueprint callable function. Let's copy this. And instead of blueprint native event, blueprint callable, this will be full override current action. And let's create a definition for this. And what we're going to do here is we are going to do something similar to what we've done here by getting the action component. So we can copy this and paste it, removing the animation montage and removing the return as well. What we're going to do now is stop current action and then get the action comp, set current action, and we will set it to this and then return true. Okay, and that should be all we need to do. Let's go ahead and compile. Oh, I had a compile error. It looks like we forgot to return false here. Let's go ahead and add that and let's try again. Okay, now what we need to do is we need to go into our hero attack. Let's add override current action. Let's copy that and paste it here in Dodge. Okay, let's try it out and see what happens. And everything seems to be working. So now action canceling is fully supported. Let's also create one more helper function to make things easier. So instead of stop action by tag, let's create a stop current action. And let's delete the action tag from here because we don't need it in stop current action. What we can do is stop current action. Now we can go to the attack animation and we can replace this with stop current action. And now we don't even have to specify a tag, which will be much easier. Okay, let's test and see if it still works. And everything is working just fine. And that brings us to the end of this flexible action system. We may expand this system more in the future, but for now, I think this is a good place to stop. We have a core action system implemented in C++ with an exposed extensibility layer in Blueprint. So we are using Blueprint and C++ together effectively. Our action system is also fully tag-based, so we can start and stop actions by tag, and we have an active tag system that allows us to grant and clear tags to the action system. And this active tag system also allows us to block certain actions from being activated if a certain tag is present in the action system. We also implemented a system to automatically handle action canceling for us, so we can easily decide to allow action canceling from one action into another. Thanks for watching. If this series was helpful to you, then be sure to like and subscribe for more videos like this.